Right now, you are not just sitting in your room, you are floating inside a hole so big it swallows 2 billion light years in every direction. And scientists are still arguing about what that means. This is not a black hole, it is something stranger, a stretch of space with far fewer galaxies than it should have. And we might be sitting almost dead center. Tonight we go inside that hole. We visit a second void, so empty it fooled astronomers for years. We follow a cold patch in the sky, older than the stars themselves. And we ask the question nobody can fully answer yet. If the universe is missing matter right where we live, what else might be missing from the story we tell about reality? If you're new here, hit subscribe, because tonight gets stranger with every chapter. Get comfortable. We begin. Picture the sky tonight. Every star you can see, every star you cannot. Now picture all of it sitting inside something empty. Not empty like a closet with nothing in it. Empty on a scale your brain was never built to hold. Scientists have a name for it, the local hole. And the wild part is this: it is not some far-off place you will never visit. You are inside it right now, reading this, breathing this, living your whole life inside it. Here is the simple version. Space is not the same everywhere. In some places, galaxies are packed close together, like houses in a crowded neighborhood. In other places, galaxies are spread thin, like a neighborhood where half the houses were never built. Our neighborhood, the one holding the Milky Way, the Sun, the Earth, and you, sits in one of the thin places, a stretch of space roughly 2 billion light-years wide, with 15 to 50% less stuff in it than the areas around it. Think about that gap for a second. If a normal patch of the universe is a packed football stadium, our patch looks like that same stadium with half the seats missing. The lights are still on. The game is still happening somewhere out there. But entire sections sit empty, and nobody expected that. Why does this matter? Because the leading model of the universe, the one taught in every science class, assumes matter is spread out fairly evenly everywhere. Zoom out far enough, and every neighborhood should look about the same. That is called the cosmological principle. It is one of the oldest, most trusted ideas in all of astronomy, and our own cosmic backyard might be breaking it. Astronomers first noticed something odd when they counted galaxies in our region of space and kept coming up short. Fewer galaxies than expected, fewer than the model said should be there. At first, this looked like a simple counting error. Telescopes miss things. Dust blocks light. Distant galaxies get missed. But the pattern held up, survey after survey. The same section of sky kept coming back emptier than it should be. But compared to what comes next, this looks calm, because this hole is not just a curiosity for scientists to argue about at conferences. It might be the missing piece in one of the biggest unsolved puzzles in modern physics, a disagreement so persistent that some researchers now call it a full-blown crisis. Two different ways of measuring how fast the universe expands give two different answers, and nobody can explain why. What if the local hole is the reason? Here's what you need to know before we go further. This void is not a theory nobody believes. Multiple research teams, using different telescopes and different methods, keep finding the same underdense region. It is not fully proven either. The exact size, the exact shape, and the exact explanation are still being debated by scientists right now, in real time, this year. That tension between something real and something not yet fully explained is exactly why this story matters. We are not talking about a settled fact from a textbook. We are talking about the edge of human knowledge, where the data hints at something big, but the full answer has not arrived yet. So hold that thought. A hole in space, roughly 2 billion light-years wide. Us, sitting somewhere near the middle of it. And a question waiting at the edge of the next chapter. How do you even find a hole that is invisible, silent, and bigger than anything the human mind was built to picture? You cannot see a void with your eyes. There is no glowing outline in the night sky that says empty space starts here. So how do scientists even know it exists? The answer starts with something surprisingly simple: counting. Imagine standing in a forest at night with a flashlight, counting trees in every direction. If one direction has way fewer trees than all the others, you would notice. Astronomers do the same thing, except instead of trees, they count galaxies, and instead of a flashlight, they use some of the most powerful telescopes ever built. When researchers counted galaxies in our cosmic neighborhood, the numbers came back wrong. Not wrong like a typo, wrong like an entire section of the map was fading out. Fewer galaxies here, fewer there. The pattern kept repeating no matter which survey they checked. Here's a comparison that makes it click. Imagine Google Maps for the universe, and instead of gaps in road data, you get gaps in galaxies. Zoom into our region, and instead of thousands of little pins marking galaxies, you get a stretch of map with barely any pins at all. Not because nobody looked, because there is genuinely less there. This creates a strange puzzle. Cosmologists build their entire model of the universe on the idea that matter spreads out evenly at large enough scales. It's one of the pillars holding up modern physics. If our neighborhood is measurably emptier than it should be, it means either our patch of space is a weird exception, or something in the model itself needs fixing. Scientists do not love exceptions. An exception nagging at the edge of a trusted model is exactly the kind of thing that keeps researchers up at night, because sometimes an exception is just noise, and sometimes an exception is the first crack in a wall that is about to come down. But here's the twist that makes this different from a simple measurement error. The missing galaxies line up with something else, something we will get to in a few chapters. A tension in how fast the universe is expanding. A tension so stubborn it has resisted every explanation thrown at it for over a decade. What if these two mysteries, the missing galaxies and the expansion puzzle, are actually the same mystery wearing two different masks? That question is what turned a simple counting exercise into one of the most talked about ideas in cosmology today. Not because scientists are certain, because for the first time, a strange gap in the data might connect to a strange gap in the theory, and connecting two mysteries is often how science finds its next big breakthrough. Farther still, in the outer reaches of this story, we meet the void by its real name, and we learn exactly how big, how deep, and how strange it actually gets. Every mystery needs a name, and this one has two. Scientists call it the local hole. Some call it the KBC void, named after the three astronomers, Keenan, Barger, and Cowie, who studied it closely back in 2013. Same place, same emptiness. Just different labels depending on who you ask. Let's build the picture piece by piece. The local hole is thought to be roughly spherical, like a ball carved out of the universe. Its size is staggering. Estimates put its radius at around 1 billion light-years. That means light, the fastest thing in existence, would need 1 billion years just to cross from the center to the edge. Here's a way to actually feel that number. If the entire history of complex life on Earth, from the first worms to right now, happened on repeat 2.5 times, that is roughly how long light takes to cross this void one way. And this is supposedly our backyard. Inside this stretch of space, matter is thinner than average. Not empty, thinner. Picture a crowded subway car during rush hour versus that same car with most of the passengers gone, just a scattered few standing near the doors. The car is not empty. It just feels strange compared to what you expect a packed train to look like. The Milky Way, our galaxy, our sun, our Earth, appears to sit somewhere near the middle of this underdense stretch. Not on the edge, not passing through, possibly right around the center of it. This is where trust signals matter. Multiple studies support the existence of an underdensity in our region. That part is well established through galaxy counts and light surveys. What remains actively disputed is the exact size, the exact shape, and whether our galaxy truly sits at the dead center. Some astronomers argue the underdensity could be explained by other factors, like dust blocking distant light, or ordinary matter that just doesn't glow enough to detect easily. So, We have a real, measured gap in the data and a genuine scientific argument about what that gap actually means. That is not a weakness in the story. That is science working exactly the way it should, testing an idea from every possible angle before accepting it. Still, here's the detail that keeps researchers hooked. If the local hole is real, and if we really do sit near its center, it would make Earth's position in the universe genuinely unusual. Not the center of everything. The universe has no center in that sense, but unusual enough that it might explain a problem that has frustrated physicists for over a decade. Because up next, we go inside the tool that made this discovery possible in the first place. A technique that lets scientists turn a flat photograph of the night sky into a full three-dimensional map, stretching billions of light years deep. Look up at the night sky and every star looks the same distance away, flat like a ceiling covered in dots. That is the biggest lie the sky tells you, because in reality, some of those points of light are millions of light years closer than others. So how do astronomers turn that flat lie into an accurate 3D map? The answer is a tool called redshift, and once you understand it, you will never look at a star the same way again. Here's the idea in plain terms. Light behaves a bit like sound. You have heard a siren change pitch as an ambulance drives past you, getting higher as it approaches, lower as it drives away. That's called the Doppler effect, and light does something similar. When a galaxy moves away from us, its light stretches out, shifting toward the red end of the color spectrum. The faster it moves away, the more the light stretches. Since the universe is expanding, almost every distant galaxy is moving away from us, which means almost every distant galaxy's light is shifted toward red. Measure exactly how much that light has shifted, and you can calculate roughly how far away that galaxy actually is. Now stack that measurement for thousands of galaxies, one by one, across a huge patch of sky. Suddenly, that flat photograph turns into something else entirely. A three-dimensional model with each galaxy placed at its true depth, not just its position on a flat image. Picture taking a single photo of a crowded parking lot from above. All the cars look flat, like they're sitting on the same level. Now imagine adding the exact distance of every car from the camera. Suddenly you can tell which cars are close, which are far, and which section of the lot is oddly empty. That is exactly what happened when astronomers ran this technique across our cosmic neighborhood. The flat image turned into a depth map, and a gap opened up right where our galaxy sits. This method is not new or shaky science. Redshift surveys have been a trusted tool in astronomy for decades, and they are how astronomers first discovered strange, empty patches of space long before the local hole ever made headlines. Which brings us to the story of the very first cosmic void ever confirmed, one so massive and so shockingly empty that it earned a nickname straight out of a horror movie. But that void, and the astronomer who stumbled onto it completely by accident, comes a little later in tonight's journey. For now, remember this: the map that revealed our hole in space was built with light, math, and a very old trick borrowed from the sound of a passing ambulance. Because the next number we're about to show you is the one that convinced scientists this was not a fluke. Every great mystery needs one number that makes everyone stop and stare. For the local hole, that number is this. Our region of space might be up to 50% less dense than the areas surrounding it. Let that sink into something real. Picture your favorite football stadium, completely packed for the championship game. Now imagine that exact same stadium with half the fans missing. Not scattered randomly, gone in specific sections, entire zones of empty seats stretching across the stands. The game still goes on, but something about the atmosphere feels fundamentally different. That's roughly the scale of what scientists are describing when they say our region of the universe is underdense, not empty, measurably thinner than it should be, based on everything the standard model predicts. Here's why a number like 50% matters so much in cosmology. Small differences in density happen everywhere. They're basically background noise. A 5% gap here, a 10% difference there. nothing to write home about. But a drop this large, in a region this massive, spanning roughly 2 billion light-years, is not something scientists can shrug off as random chance or a fluke in the data. The standard cosmological model has a rule baked into its foundation. At large enough scales, matter spreads out evenly. Zoom out far enough, and every corner of the universe should look roughly the same as every other corner. That rule has held up remarkably well for decades of observations. A 50% underdensity, right where we happen to live, does not break that rule completely, but it stretches it about as far as it can go before something has to give. So scientists faced a choice. Maybe we got unlucky, and we just happened to live in one of the rare emptier patches of the universe, purely by chance. Or maybe this underdensity is a clue pointing towards something deeper, something the standard model has not fully accounted for yet. Here's the trust signal worth holding on to. The underdensity itself is measured and confirmed across several independent surveys. What remains a genuine, ongoing debate is why it exists, and what it actually means for our broader picture of the cosmos. And this is exactly where the story shifts from strange to seriously significant, because this same underdense region does not just sit there quietly being unusual. It might be directly connected to one of the most stubborn, most talked about problems in modern physics, a disagreement between two different measurements of the universe that has frustrated scientists for well over a decade. Farther still, we're about to see exactly how big 2 billion light-years really feels, using comparisons your brain can actually hold on to. Numbers like 2 billion light-years and 50% underdense are easy to say and almost impossible to actually feel. So let's slow down and build a picture your brain can hold on to. Start small. Imagine driving across your entire state on a long road trip, hours and hours of highway, mile markers ticking past. Now imagine that same road trip, except every so often, entire stretches of road simply have nothing around them. No houses, no gas stations, no trees. Just flat, empty land for miles at a time, then a small town, then emptiness again. That patchy, uneven feeling is roughly what the large-scale universe looks like. Dense clusters of galaxies, connected by long strands, surrounded by enormous stretches of near-nothing. Scientists call this pattern the cosmic web, and we will explore it properly in a later chapter. For now, just picture that half-empty highway. Now, here's where it gets personal. Our galaxy does not sit in one of the crowded towns along that highway. We sit out on one of the empty stretches, a very, very long empty stretch, roughly 2 billion light-years across, with noticeably fewer galaxies scattered through it than the crowded regions nearby. Try this comparison. If the entire visible universe were shrunk down to the size of a football field, our local underdense region would still stretch across a meaningful chunk of that field, not just a corner. This is not a pothole in the road. This is a significant stretch of empty highway, and we are parked somewhere near the middle of it. Here's the piece that should genuinely unsettle you a little. For most of human history, people assumed Earth's location in the universe was completely unremarkable. Just an average galaxy, in an average neighborhood, nothing special about our address in space. That assumption has a name, the cosmological principle, the same rule we mentioned back in Chapter 1. If we really do sit near the center of a significant underdensity, our address might not be quite as average as we thought. Now, does this mean Earth is special, chosen, or important in some cosmic sense? Scientists are very careful here, and so should we be. Being in an unusual location does not mean being important. It just means the data does not perfectly match the simplest version of the model, and that mismatch is worth investigating. But investigating this mismatch is exactly what led scientists toward one of the strangest unsolved puzzles in all of physics. A puzzle involving two clocks, both measuring the same universe, both giving two different answers. That puzzle is coming up next, and once you understand it, you will see exactly why this empty stretch of space might matter more than anyone expected. Here's a rule scientists have trusted for almost a century. Zoom out far enough, and the universe should look the same no matter which direction you point your telescope. same density of galaxies, same overall structure, no special corners, no favored neighborhoods. This idea has a name, the cosmological principle, and it is one of the load-bearing walls of modern physics. Think of it like this. Imagine a giant bowl of soup, evenly stirred, with vegetables spread throughout. Scoop out a spoonful from the top, the bottom, the left side, the right side. It should not matter. Every spoonful looks roughly the same. That is what scientists expect from the universe at the largest scales. For decades, this idea worked beautifully. Every big survey of the sky supported it. Galaxies clustered here, thinned out there, but on average, across huge enough regions, everything balanced out. The soup looked evenly stirred. Then researchers pointed their instruments at our own neighborhood and got a spoonful that looked different from the rest of the bowl. Here's why that single spoonful matters so much. If the universe really is evenly stirred everywhere, then finding a meaningfully empty patch exactly where we happen to live should be incredibly rare, almost suspicious. Either we got extraordinarily unlucky, landing in one of the rare thin spots purely by chance, or something about the model itself needs a second look. Scientists have run the numbers on that bad luck explanation, and the odds are not comfortable. A void as large and as empty as ours, sitting exactly where our galaxy happens to be, is the kind of coincidence that makes researchers deeply suspicious of coincidence. But compared to what comes next, this still looks calm, because here's the twist. This is not the first time astronomers have found an enormous empty patch that seemed to defy the model. Decades earlier, one astronomer stumbled onto an even stranger void completely by accident, one so massive and so shockingly empty that it earned a nickname straight out of a horror movie. We will step inside that story soon. For now, hold on to this one idea. The cosmological principle says, our spoonful of universe should look average, ours does not. And that single mismatch opened the door to one of the most talked about disagreements in modern physics. A disagreement about the exact speed at which the entire universe is expanding. Two different methods, two different answers, and a hole in space that might explain why. Here's something that sounds like science fiction, but is actually just physics. Living inside a hole in space can change how fast the universe appears to be expanding around you. Not because the void is doing anything magical, because of gravity and how gravity behaves near the edges of empty space. Let's build this slowly. Gravity is not just the force that keeps your feet on the ground. On a cosmic scale, gravity constantly pulls galaxies toward each other, especially toward regions packed with more mass. Dense areas act like magnets, tugging surrounding matter toward them. Now picture a void, a region with less matter than average, surrounded by denser walls of galaxies on every side. Anything sitting inside that void experiences an unusual kind of pull. The dense walls around the edges tug outward in every direction, like a rubber band stretched from the inside. Here's a comparison that makes it click. Imagine standing in the middle of an empty parking lot, with crowds of people pulling you gently outward from every direction at once, toward the edges of the lot. You would feel pulled apart in a way that someone standing in a packed crowd never would. Galaxies inside a void experience something similar. The uneven pull from the denser surrounding regions can make the void itself appear to expand a little faster than the universe as a whole. Not because space itself is behaving differently in that spot, because the local gravity math changes when you are sitting inside a bubble of emptiness surrounded by walls of matter. This detail matters enormously, because it means an observer living inside a large void, someone like us, might measure the universe expanding at a different local rate than an observer living in a denser part of the cosmos would measure. Here's the trust signal to hold on to. This mechanism, void interiors experiencing a locally faster expansion rate, is well supported by both theory and simulations. What remains genuinely debated is whether our local underdensity is large enough and deep enough to fully explain the specific expansion mismatch scientists have been wrestling with for years. That mismatch has a name, and it has become one of the most persistent headaches in modern cosmology. Farther still, we are about to meet that mismatch directly, and once you understand it, this entire hole in space story clicks into place. Every physicist agrees the universe is expanding. Nobody disputes that. The argument is about exactly how fast, and that argument has a name, the Hubble tension, and it might be the biggest unresolved puzzle in cosmology today. Here's the simple version. Scientists have two completely different ways of measuring how fast the universe expands. One method looks at light from the early universe, the leftover glow from moments after the Big Bang. The other method looks at nearby stars and galaxies, using them like mile markers to measure expansion in our local neighborhood. Both methods are trusted. Both methods have been refined for decades. Both methods should, in theory, give the same answer, since they are measuring the exact same universe. They do not. The early universe method consistently gives a slower expansion rate. The local, nearby galaxy method consistently gives a faster one, not by a tiny, forgettable margin either. The gap is large enough and stubborn enough that scientists have ruled out simple measurement error as the explanation. Picture two different clocks, both supposedly showing the exact same time zone, both carefully calibrated by expert clockmakers. Except every single time you check them, one clock reads a few minutes ahead of the other, not randomly, consistently. Every single time. At some point, you stop assuming it's a broken clock and start wondering if something deeper is going on. That is exactly the situation cosmologists are stuck in. Two trusted, well-calibrated methods consistently disagreeing. Here's why this problem has scientists genuinely on edge. If the disagreement was random noise, it would have faded away as instruments improved over the years. Instead, as telescopes got sharper and measurements got more precise, the gap between the two answers stayed just as stubborn, sometimes even growing slightly more pronounced. This is not a minor rounding error buried in a physics textbook. This is a fundamental crack in how confidently we understand the expansion history of the entire universe. And here's where our hole in space walks back into the story. Remember the last chapter, where we explained that living inside a void might cause the local expansion rate to appear artificially faster? What if that is exactly what's happening to us? What if the local hole is quietly warping our local measurement, creating a mismatch that has nothing to do with the early universe being wrong and everything to do with our own address in space? That single idea has become one of the most exciting possible explanations for the Hubble tension in the last several years. But compared to what comes next, even this looks like the calm chapter. Because we are about to meet two very different scientific camps, each offering their own answer to this exact mystery, and their disagreement runs deeper than you might expect. Let's slow all the way down and really look at these two clocks, because understanding them is the key to understanding everything else in this story. Clock number 1 measures the universe using its oldest light. Right after the Big Bang, the universe was an unbelievably hot, dense soup. Roughly 400,000 years later, it cooled enough for light to finally travel freely through space for the first time. That ancient light is still out there today, stretched out by billions of years of cosmic expansion, and scientists can detect it. It's called the cosmic microwave background, and it acts like a fossil snapshot of the baby universe. By studying tiny patterns hidden inside that ancient light, scientists calculate how fast the universe should be expanding today, based on how everything has unfolded since the very beginning. Clock number 2 works completely differently. Instead of looking backward at the beginning of everything, it looks at objects nearby, like exploding stars called supernovae and pulsing stars called Cepheid variables. These act like reliable mile markers, since scientists know roughly how bright they truly are versus how bright they appear from Earth. Comparing true brightness to apparent brightness reveals distance. Track enough of these mile markers, and you can directly measure how fast nearby space is stretching apart. Right now, in our own cosmic backyard, here's the comparison that makes this click. Clock 1 is like reading a 100-year-old letter that describes exactly how fast a river used to flow at its source. Clock 2 is like standing at the riverbank today with a stopwatch, measuring the current flow speed directly. Both approaches should describe the same river. Both should agree. They don't. Clock 1, the ancient light, consistently predicts a slower expansion rate. Clock 2, the nearby mile markers, consistently measures a faster one. The gap sits right around 10%, which sounds small until you realize an entire universe rests on getting this number exactly right. Trust signal time. This disagreement is not a hypothesis. It is a measured, repeated, well-documented result, confirmed across dozens of independent studies using different instruments and different teams. What remains genuinely unresolved is the explanation behind it. Some scientists think the early universe method might be missing something subtle from the ancient light itself. Others think the nearby method might have a hidden bias in how it measures those stellar mile markers. And a growing number of researchers think the answer might not be a flaw in either method at all. What if both clocks are actually correct, and the real explanation is that we live somewhere unusual, somewhere that makes the local clock run just a little differently than the rest of the universe? That idea leads directly back to our hole in space. And next, we explore exactly how seriously scientists are taking it. Here's the idea that turned a strange local void into one of the most talked about explanations in modern cosmology. What if the Hubble tension is not a flaw in either measurement method at all? What if it is simply a side effect of where we happen to live? Let's connect the pieces we've built so far. We know our region of space appears to be significantly underdense, possibly by as much as 20% compared to the universe's overall average. We know galaxies sitting inside underdense regions can experience a locally faster expansion rate, purely because of how gravity pulls differently near the edges of a void. And we know one of our two expansion clocks, the nearby one, measures a faster rate than the other. Put those three pieces together, and a striking possibility appears. What if the local clock is not wrong at all? What if it is accurately measuring a real local speed-up, caused entirely by us sitting inside this enormous, underdense stretch of space? Under this idea, the ancient light clock stays completely correct, describing the true expansion rate of the universe as a whole. The nearby clock also stays completely correct, describing what things genuinely look like from inside our unusual neighborhood. Neither measurement is broken. We simply live somewhere that makes the local number look different from the global one. One physicist studying this exact idea put it clearly. The tension appears largely as a local phenomenon, with far less evidence that the expansion rate disagrees with standard predictions once you look much farther back in time. In other words, the problem seems to live right here, in our own cosmic backyard, rather than in the universe's ancient past. Here's why this idea excites so many researchers. It does not require inventing brand new physics or breaking any previously trusted laws. It simply requires our specific address in space to be a little less average than the standard model originally assumed. But here's the honest trust signal, and it matters. This remains an active, unresolved area of genuine scientific debate, not a settled conclusion. For a local void explanation to fully account for the Hubble tension, our underdensity would likely need to be deeper and possibly larger than some current measurements suggest. Several research teams are actively testing whether the numbers truly add up, and the community remains split. If they do add up, this becomes one of the most elegant solutions to one of physics' most stubborn problems in decades. If they don't, the Hubble tension stays wide open, and something even stranger might be waiting underneath it. Either way, this single idea has pulled physicists toward an unexpected place, reconsidering not just how fast the universe expands, but reconsidering the very rules of gravity itself. That reconsideration is exactly where we head next. Every explanation so far has assumed one thing without question: that gravity works exactly the way Isaac Newton and Albert Einstein described it, everywhere, always. But a small, persistent group of physicists have spent decades asking an uncomfortable question. What if gravity itself behaves slightly differently than we assume, especially in regions with extremely low density, like the middle of a void? Here's why that question even exists. Standard gravity works incredibly well at explaining how planets orbit stars, how moons orbit planets, how everyday objects fall. But zoom out to the scale of entire galaxies, and something strange happens. Galaxies spin faster than standard gravity alone can explain. Given the visible matter we can actually detect inside them, the mainstream fix for this puzzle is dark matter, invisible material that adds extra gravitational pull without giving off any light we can see. Most of the scientific community strongly supports this explanation, and there's substantial supporting evidence behind it. But a smaller group of researchers proposes something different. What if there is no invisible matter filling the gap at all? What if gravity itself simply behaves differently once you get to these enormous, ultra-low density scales, and our equations just haven't caught up yet? Picture pushing a shopping cart across a smooth tile floor, then pushing that exact same cart across thick, plush carpet. Same cart, same amount of push, but the cart behaves differently depending on the surface underneath it. This alternate idea suggests gravity itself might behave a little differently depending on the surface of density it's operating within, especially at the extremely low densities found deep inside a massive void. This alternate theory has a name, and it's directly connected to our local hole in space story. Some researchers studying the local hole have found that factoring in this different version of gravity, alongside the underdense region we live in, helps the numbers line up even more convincingly with the Hubble tension puzzle. Here's the honest trust signal, because this part matters enormously. This alternate gravity idea remains a genuine minority position within physics. The vast majority of cosmologists still favor the standard model, combined with dark matter, as the better supported explanation for galaxy behavior. But the fact that this alternate idea keeps connecting back to our specific local void, strengthening the possible explanation for the Hubble tension, has kept it firmly in the conversation rather than dismissed entirely. Next, we give this alternate idea its full name, and we explore exactly how it proposes rewriting one of the most fundamental forces in the entire universe. It has a complicated name, but stick with it, because the idea underneath is simple. Modified Newtonian dynamics, often shortened to MOND, is a theory proposed roughly 4 decades ago as an alternative explanation for why galaxies spin faster than standard gravity alone predicts. Here's the standard story first, for comparison. Most physicists explain the extra spin using dark matter, an invisible substance that adds extra gravitational pull throughout a galaxy, without emitting any light our telescopes can detect. Under this view, galaxies spin fast because there is more mass present than we can directly see, simple as that. MOND takes a completely different approach. Instead of adding invisible matter, it suggests that gravity itself changes its behavior once the gravitational pull becomes extremely weak, like the pull found in the outer edges of galaxies, or deep inside a massive, underdense void. Here's a comparison to make this click. Imagine a car that drives normally on the highway, following all the expected rules of speed and acceleration. Now imagine that same car entering an extremely low-friction, icy back road, and suddenly, it behaves in ways that don't match the highway rulebook at all. Standard gravity is your highway rulebook. MOND suggests that in extremely weak gravity environments, the vehicle switches to different rules entirely. Under MOND, you don't need invisible matter to explain a galaxy's fast spin. You simply need gravity itself to behave slightly differently once it gets weak enough. This idea connects directly back to our void story. Remember, the interior of a massive underdense region, like the local hole, is exactly the kind of extremely low gravity environment where MOND's modified rules would matter most. Some researchers combining MOND with our local underdensity have found the Hubble tension numbers line up more convincingly than either idea manages entirely on its own. Here's the necessary trust signal, and it's an important one. MOND remains a minority position in physics, actively debated rather than broadly accepted. It explains certain galaxy behaviors impressively well, but struggles to match other types of observations, like how galaxy clusters behave, nearly as cleanly as the standard dark matter model does. Most cosmologists still favor dark matter as the stronger, better supported explanation overall. But here's why MOND stays relevant to our story specifically. Whether or not it turns out to be the correct description of gravity everywhere, it keeps showing up as a useful tool exactly where our void story lives, in the deep, quiet interior of massive underdense regions like the one surrounding us. Farther still, we leave gravity behind for now, and we travel to a completely different void, one discovered decades earlier, so shockingly empty, it earned a nickname straight out of a horror film. Before we travel to our next void, let's pause and really absorb what we've built so far, because the next chapters escalate fast, and this foundation matters. We started with a simple, unsettling fact. Our cosmic neighborhood appears to be measurably emptier than the universe's average. We learned scientists build 3D maps of the sky using stretched light, revealing exactly where these empty regions hide. We discovered that living inside a void can locally speed up the apparent expansion of space, purely through uneven gravitational pull along the void's edges. That single mechanism connects directly to the Hubble tension, one of the most stubborn open problems in modern physics. Two trusted measurement methods, consistently disagreeing about how fast the universe expands. And we explored two very different possible explanations. One where standard gravity stays exactly as Einstein described it, and our unusual local address alone explains the mismatch. Another, more radical option, where gravity itself might behave differently at extremely low densities, an idea called modified Newtonian dynamics. Here's the honest state of the story right now. Nobody has definitively solved the Hubble tension yet. Multiple explanations remain on the table, actively studied, actively debated, actively tested against new data as better telescopes come online. That is not a disappointing ending. That is what real, unfinished science actually looks like. But here's what makes tonight's story special. Our local hole is not the only void of its kind ever discovered. It's not even the first. Decades before scientists mapped our specific underdense neighborhood, an astronomer stumbled onto a completely different void, one so massive and so shockingly empty that it fundamentally changed how scientists thought about the structure of the entire universe. That discovery happened almost completely by accident, buried inside a routine survey nobody expected to reveal anything unusual at all. We're about to meet it directly. And once you understand exactly how empty it truly is, our own hole in space might start to feel almost ordinary by comparison. In 1981, an astronomer named Robert Kirshner was not hunting for a giant hole in space. He was running a fairly routine survey, measuring the redshift of galaxies in one specific patch of sky in the direction of a constellation called Boötis. Standard work, careful, methodical, unglamorous. Then the data came back, and something was very wrong. In that patch of sky, where his team expected to find roughly 100 galaxies based on typical cosmic density, they found only 3. Read that number again, not a smaller amount. 3 galaxies where about 100 should have been. At first, everyone assumed a mistake, bad calibration, missed detections, dust blocking distant light. Kirshner's team checked everything, ran the numbers again, and the emptiness held firm. This was not an equipment glitch. This was a genuinely, dramatically empty region of space, hiding in plain sight the entire time. Follow-up surveys expanded the search area, and the picture only got stranger. Across the full volume of this newly discovered region, scientists expected somewhere around 2,000 galaxies based on average cosmic density. They found roughly 60. Here's a comparison that makes that gap feel real. Picture a massive stadium built to comfortably hold 2,000 people for a concert. Now picture that exact same stadium with only 60 people scattered across the seats. A handful of fans near the front, a few more near the exits, and the rest of the entire stadium sitting completely, eerily empty. This region earned an early nickname that stuck around for years: the Great Nothing. Eventually, it became known officially as the Boötes Void, named simply after the constellation it appeared within. Here's the trust signal worth holding on to. Unlike some of the more debated ideas we covered earlier tonight, the Boötes Void is not controversial. It is confirmed, extensively studied, and considered one of the largest, best documented voids ever discovered in the observable universe. And its size is almost impossible to properly picture, which is exactly where we're headed next. Let's actually sit inside the scale of the Boötes Void for a moment, because the raw numbers deserve more than a quick mention. The void stretches roughly 330 million light-years across. That number alone barely means anything until you compare it to something familiar. Our own galaxy, the Milky Way, spans roughly 100,000 light-years from edge to edge. That means the Boötes Void could swallow the entire Milky Way and fit it inside itself thousands upon thousands of times over, with room left to spare. Here's a comparison that might land even harder. Picture the distance between New York and Los Angeles, roughly 2,400 miles. Now imagine needing to repeat that exact same coast-to-coast trip more than 80,000 times in a row just to cross the Boötes Void once, from one side to the other, and inside that entire, almost incomprehensible volume of space, only 60 confirmed galaxies exist. One astronomer studying the void, Greg Aldring, put the emptiness into a genuinely chilling perspective. If our own Milky Way had happened to form at the exact center of the Boötes Void instead of where it actually sits, humanity would not have discovered the existence of other galaxies until sometime in the 1960s. Not because the technology wasn't ready, because there simply would have been nothing else close enough to detect for the majority of human history. Sit with that for a second. An entire civilization, developing telescopes, developing astronomy, developing every branch of physics, all while looking out into what appeared to be a truly empty universe, with no other galaxies visible anywhere nearby. Here's the honest scientific detail worth keeping straight. The void isn't a perfect, mathematically flawless vacuum. A small number of real, confirmed galaxies do exist, scattered somewhere inside it, discovered gradually across multiple follow-up surveys throughout the 1980s and 90s. But compared to the roughly 2,000 galaxies a typical volume that size should statistically contain, 60 is still an almost unbelievable gap. This raises an unavoidable question. If a hole this massive, this genuinely empty, can exist hiding in plain sight for years before anyone even noticed, what does that mean for our confidence in mapping the rest of the universe? Farther still, we step inside exactly what it might feel like to actually live inside a void this size, seen from the perspective of a civilization trapped right at its very center. Let's run a thought experiment, because this is where the Boötes Void stops being just an abstract number and starts feeling genuinely unsettling. Imagine an alternate version of Earth, orbiting an alternate version of the Sun, sitting at the dead center of the Boötes Void, instead of where our real solar system actually formed. Same physics, same laws of nature, same curious species, eventually evolving, building telescopes, staring up at the night sky, asking the exact same questions we ask today. What would their night sky actually look like? Mostly dark, genuinely, overwhelmingly dark. A few scattered points of light from the handful of nearby galaxies within the void, but nothing resembling the rich, busy sky we're used to. No dense clusters, no bright galactic neighbors nearby, just isolated points of light, scattered unbelievably far apart from one another. For that alternate civilization, the biggest scientific debates of their early history might look completely different from ours. They might spend centuries assuming their own galaxy was the only one that existed anywhere in the universe, not through a lack of curiosity or effort, simply because, from their exact vantage point deep inside that emptiness, there would be nothing else close enough or bright enough to convincingly detect. Only with dramatically more powerful telescopes, capable of reaching much farther out toward the void's distant edges, would they finally begin detecting other galaxies at all. And by that point in their scientific history, they might have already built entire theories of the cosmos, assuming their galaxy was fundamentally alone. Here's why this thought experiment actually matters for our own reality, and it's not just a fun mental exercise. It's a genuine reminder that where you happen to be born, quite literally, shapes what you're capable of discovering. Our own view of the universe, right now, tonight, is shaped by our specific cosmic address. We happen to sit somewhere with enough nearby galaxies to piece together concepts like the cosmic web, galaxy clusters, and enormous voids like Boötes. An observer sitting in a different neighborhood might have a radically different picture of reality, built from radically different available evidence. This raises an uncomfortable question worth sitting with, at least for a moment. If our specific location shapes what we're capable of seeing, and shapes what theories we're even capable of imagining, how much of our current picture of the universe is genuinely universal truth, and how much is simply a reflection of exactly where we happen to be standing? We don't have a complete answer to that question. Nobody does yet. But it's exactly the kind of question that keeps cosmologists working late into the night. And it's exactly the kind of question that leads us toward our next destination, the actual tool that lets scientists find Boötes in the first place, and the strange cosmic structure it revealed once fully mapped out. Every great discovery has a human moment behind it, and the story of the Boötes void has one worth telling properly. Robert Kirshner was not chasing fame. He was not trying to break cosmology. He was simply doing careful, patient survey work, measuring redshifts, one galaxy at a time, across a specific patch of sky. Here's what makes this story stick. Kirshner worked alongside 3 other astronomers, Augustus Oehmler, Paul Schechter, and Stephen Schechtman, running what should have been a fairly routine project. Measure distances, build a map, publish the results, move on to the next patch of sky. Instead, the numbers came back so strange that the team had to stop and question everything. When something looks broken, the first instinct in science is never, "we discovered something incredible." The first instinct is always, "we probably made a mistake somewhere." So they checked, and checked again. They re-examined their instruments, their calibration, their methods for identifying galaxies. Every possible source of error got tested. And every single time, the emptiness held firm. In 1981, they published a short paper describing what they'd found. Not a triumphant announcement of cosmic revolution, just a careful, restrained scientific report describing a patch of sky with dramatically fewer galaxies than expected. Here's the part that deserves real respect. A short paper like that could have easily been ignored, buried among thousands of other astronomy papers published that same year. Instead, other astronomers took notice, and follow-up surveys began confirming and expanding the discovery throughout the rest of the decade. By 1987, a fuller survey mapped the region in far greater detail, cementing what became known as the Boötes void as one of the most significant structural discoveries in modern astronomy. Here's the trust signal worth remembering. This entire discovery holds up as one of science's cleanest examples of the process working exactly as intended. An unexpected result. Careful, repeated verification. Independent confirmation from other research teams. No shortcuts. No premature announcements. And this discovery didn't just reveal one enormous empty region floating alone in space. It became one of the earliest pieces of evidence supporting an entirely new way of picturing the universe's large-scale structure. Not scattered randomly, like stars sprinkled across black paper. Something far more organized. Something that looks, almost eerily, like a web. That structure is exactly where we're headed next. And once you see it clearly, you'll never picture the universe as simple, empty space again. Let's take a step back and really look at the shape of what we've uncovered so far tonight, because the picture is about to get much bigger. We have 2 confirmed regions of dramatically empty space. Our own local hole, roughly 2 billion light-years across, sitting right where we happen to live. And the Boötes void, roughly 330 million light-years across, discovered decades earlier through nothing more than careful, patient survey work. Here's the question that should be forming in your mind right now. If two separate, independently confirmed voids exist, genuinely massive stretches of near-empty space, what does the rest of the universe actually look like at this same enormous scale? The answer turns out to be genuinely surprising, and it reshapes everything we thought we understood about how galaxies are arranged. Picture ocean foam for a second, the kind you'd see after a wave crashes onto rocks. Foam isn't a random scattering of bubbles floating independently in every direction. It's structured. Bubbles connect to other bubbles. Thin walls of liquid separate one pocket of air from the next. Empty pockets sit surrounded by thinner, denser boundaries holding everything together. The large-scale universe looks remarkably similar to that foam, just built from galaxies instead of soap and water. Dense regions, packed full of galaxies, form long, connected strands stretching across enormous distances. Between those strands sit enormous empty pockets, voids like our own local hole and like Boötes, surrounded by these thinner walls of galaxies holding the entire structure together. This isn't a loose metaphor invented just for tonight's story. This is an actual, scientifically mapped structure, confirmed through decades of redshift surveys, just like the ones we described earlier. Scientists gave this cosmic structure an official name. They call it the cosmic web. Here's the trust signal worth remembering as we move forward. The cosmic web is not a disputed theory. It is one of the most thoroughly confirmed structures in all of modern astronomy, mapped repeatedly through independent surveys spanning decades, using different telescopes, different methods, and different research teams, all converging on the exact same underlying pattern. Our own local hole and the Boötes void are not strange, isolated exceptions floating alone somewhere in an otherwise uniform universe. They're simply two visible examples of the empty pockets woven directly into this much larger, web-like structure. But compared to what comes next, even the full picture of the cosmic web only tells half of tonight's story. Because next, we zoom out even further, and we look at exactly how much of the entire universe's volume is actually taken up by empty pockets, just like these. Let's properly meet the structure holding this entire story together, because everything we've explored tonight, our own hole in space, the Boötes void, even the Hubble tension itself, all connects back to this one underlying pattern. The cosmic web is built from four main types of structure, and once you picture each one clearly, the entire universe starts to look completely different in your mind. First, voids. Vast, underdense pockets of near-empty space, like the two we've already explored tonight. Second, filaments. Long, thread-like strands of galaxies stretching across enormous distances, connecting denser regions together like strands of a spider's web. Third, walls. Flatter, sheet-like regions of galaxies forming boundaries between neighboring voids. Fourth, nodes. Incredibly dense clusters sitting at the intersections where multiple filaments meet, often containing thousands of galaxies packed tightly together in one location. Here's a comparison that makes this click immediately. Picture an actual spider's web glistening with morning dew. Thin strands stretch between anchor points, and wherever multiple strands cross paths, you get a stronger, reinforced junction. Empty air fills every open pocket between the strands. Now replace every strand with a chain of galaxies stretching across millions of light years, and replace every empty pocket of air with an enormous cosmic void. That's essentially what astronomers mean when they describe the shape of the universe. Here's what makes this structure genuinely humbling. Filaments, these connecting strands of galaxies, can stretch across several 100 million light years in length, and they're not the exception in how galaxies are arranged. They're the rule. The vast majority of galaxies throughout the observable universe sit somewhere along this vast filamentary network, rather than floating independently in random, isolated locations. Nodes, meanwhile, represent the polar opposite extreme. These are the places where filaments physically intersect, and the density found there can reach many times higher than the universe's overall average, hosting massive galaxy clusters containing potentially thousands of member galaxies crammed into a relatively compact region of space. Here's the trust signal to hold on to tonight. This four-part structure, voids, filaments, walls, and nodes, is not a rough sketch or a simplified metaphor for public consumption. It's a rigorously confirmed picture, built from decades of redshift surveys, and more recently, sharpened even further using extraordinarily detailed observations from the James Webb Space Telescope. Recent Webb telescope surveys have reconstructed this exact web-like structure, reaching all the way back to when the universe was less than 1 billion years old, revealing that this fundamental pattern, dense strands surrounding enormous empty pockets, has existed for the overwhelming majority of cosmic history, which raises an almost dizzying question. If this pattern has held steady for billions of years, exactly how much of the universe's total volume actually belongs to these empty pockets, compared to the strands and nodes connecting everything together? That specific number is coming up next, and it might be larger than you're expecting. Here's a number that deserves its own moment of silence before we even try to unpack it. Based on current cosmic web research, voids are estimated to occupy roughly 80% of the entire universe's total volume, while containing only around 20% of its total mass. Read that gap again slowly. 80% of all available space, holding just 20% of all available matter. Here's a comparison that might finally make that number feel real. Picture your entire house, every single room combined. Now imagine that 80% of your home's total floor space is completely empty rooms, while every single piece of furniture, every book, every belonging you own, gets crammed into the remaining 20%. That's roughly the ratio we're talking about here, except applied to the entire observable universe instead of just your house. This means something genuinely unsettling once you fully absorb it. The universe, at its very largest scales, is overwhelmingly, dominantly empty. Galaxies, stars, planets, and everything else we typically picture when we imagine the universe are actually the exception, not the rule. They're clustered into a relatively small fraction of the total available space, while the vast majority of everything that exists is emptiness. Here's another number worth sitting with. Typical voids throughout the universe measure somewhere between 30 and 150 megaparsecs across, which translates to roughly 100 to 500 million light-years in diameter. That means voids similar in scale to Boötes are not some incredibly rare, one-of-a-kind cosmic anomaly. They represent a completely normal, expected feature of how the universe is fundamentally structured. Here's the detail that connects everything we've covered tonight back together into one unified picture. Voids don't just sit there passively, existing as empty, leftover space between denser regions. They actively expand faster than the universe's overall average rate, precisely because of that same uneven gravitational pull we described several chapters back, where dense surrounding walls tug outward on anything sitting inside an underdense pocket. Our own local hole, the Boötes void, every single void woven throughout this vast cosmic web, all of them, quietly, gradually growing a little faster than the rest of the universe around them, every single day. Here's the trust signal worth holding onto as we move forward. These specific percentages come directly from peer-reviewed cosmological research, and they represent genuinely well-established science, not speculation or rough guesswork. What remains actively studied and debated is precisely how these voids first formed, and precisely how they continue evolving as the universe keeps aging and expanding. We've now built the full picture, our own hole in space, a void from decades past, an entire universe dominated by emptiness. But tonight's story isn't finished yet, because there's one final mystery waiting. A cold, ancient patch hiding directly in the sky above you, and it might connect to everything we've explored so far in a way that should genuinely give you chills. Every so often, cosmologists find something in the data that simply should not be there, something that doesn't fit cleanly into any existing explanation. The CMB cold spot is exactly that kind of anomaly, and it's been quietly puzzling scientists for over 2 decades. Remember the cosmic microwave background from a few chapters back? That ancient leftover light from roughly 400,000 years after the Big Bang? Scientists have mapped that ancient light across the entire sky in extraordinary detail, and across almost the entire map, the temperature stays remarkably consistent, varying by only the tiniest possible fractions, except in one specific spot. In the direction of a southern constellation called Eridanus, there's a patch of this ancient light that runs noticeably colder than everywhere else surrounding it. Not by a huge amount in absolute terms, but by far more than random statistical variation should ever reasonably produce. Here's why cosmologists take this so seriously. The cosmic microwave background is supposed to behave like statistical noise once you account for the universe's expected well-understood ripples and fluctuations. A patch this cold, standing out this clearly from its surroundings, is roughly equivalent to flipping a coin repeatedly and getting the same unlikely result far more often than pure chance should ever allow. Here's a comparison that makes this click. Imagine a massive room completely filled with people, all standing at roughly the same, comfortable, consistent body temperature. Except in one specific corner of that room, a group of people are measurably, noticeably colder than absolutely everyone else present. You wouldn't just shrug that off as random chance. You'd want to know exactly why that specific corner is different. Scientists have been asking that exact same question about the cold spot for over 20 years now, ever since it was first properly identified back in 2005. Here's the trust signal worth remembering. The existence of the cold spot itself is not seriously disputed. It's been repeatedly confirmed across multiple independent sky surveys using different instruments. What remains genuinely, actively debated is the underlying cause behind it. And here's where tonight's entire story finally, dramatically, comes full circle. Because sitting almost perfectly aligned with this cold, mysterious patch in the ancient sky, scientists eventually discovered something else entirely. Another massive void, another enormous stretch of underdense, near-empty space. That void has a name, and its story is about to bring everything we've explored tonight together into one final, unforgettable picture. Scientists suspected for years that an enormous void might be sitting directly in the path of the cold spot, hiding somewhere between Earth and that ancient light, but confirming it required a level of precision that simply didn't exist yet. That changed with the Dark Energy Survey, one of the most ambitious galaxy mapping projects ever undertaken. Using a massive telescope perched high in the Andes Mountains of Chile, researchers used this survey to map, with genuine confidence, the exact region of space sitting directly along our line of sight toward the cold spot. What they found was staggering. A massive, elongated void stretching roughly 1.8 billion light-years across, containing measurably less matter, roughly 30% less, than the universe's overall surrounding average. Scientists named it the Eridanus supervoid, matching the constellation where it appears in our sky. Here's a comparison that helps this scale actually land. If you tried crossing the Eridanus supervoid at the speed of light, the fastest possible speed in the entire universe, the trip would still take you nearly 2 billion years, one direction, without stopping. Here's why its exact position matters so enormously to this story. The Eridanus supervoid sits almost perfectly aligned with the cold spot, positioned directly along the same line of sight from Earth. That precise alignment is not the kind of coincidence scientists dismiss easily. The proposed explanation connects back to a concept we touched on earlier tonight. As ancient light from the ancient universe travels toward us, it has to pass directly through this enormous underdense region along the way. Passing through a genuine void can very slightly alter that ancient light's temperature through a subtle physics effect, before that light ever reaches our telescopes. If the Eridanus supervoid is large enough and deep enough, Some of that cold spot's chilly temperature might be explained simply by ancient light traveling straight through a very large, very empty patch of space on its long journey toward Earth. Here's the honest trust signal, and it genuinely matters here. Researchers have confirmed the Eridanus supervoid is real, and confirmed it sits correctly aligned with the cold spot. But current calculations suggest the void, on its own, only accounts for somewhere between 10 and 20% of the cold spot's total observed temperature drop, not the full explanation. A meaningful piece of a still larger, still unsolved puzzle, which means the full mystery of the cold spot remains genuinely open. And that open question is exactly where we're headed next. Let's really sit inside the true scale of Eridanus for a moment, because a number like 1.8 billion light-years deserves more than a passing mention. Our own local hole stretches roughly 2 billion light-years across. The Boötes void measures roughly 330 million light-years. Eridanus lands somewhere impressively close to our own local hole in overall scale, making it one of the largest confirmed voids scientists have ever mapped anywhere in the observable universe. Here's a comparison worth holding on to. If the entire, roughly 93 billion light-year width of the observable universe were compressed down into a single cross-country road trip stretching the length of the United States, the Eridanus supervoid alone would still stretch across a noticeable, meaningful chunk of that entire journey, not a pothole in the road. A significant, sprawling stretch of genuinely empty highway. Here's what makes Eridanus scientifically distinct from the other voids we've explored tonight. Unlike a perfectly round, symmetrical sphere, Eridanus appears noticeably elongated, stretched out along our specific line of sight from Earth, almost like a cigar shape drifting through space. Researchers describe its exact underlying structure as genuinely complicated, likely composed of several smaller, interconnected subvoids rather than one single, perfectly uniform empty region. Here's the piece that connects everything we've built tonight together into one unified picture. We now have solid, independently confirmed evidence of at least 3 separate massive voids. Our own local hole, sitting right where we live, the Boötes void, discovered decades earlier through careful, patient survey work, and now Eridanus, aligned precisely with one of the strangest anomalies ever detected in the universe's oldest surviving light. 3 separate voids, 3 completely independent discoveries, all pointing toward the exact same underlying truth. Emptiness is not the rare exception scattered occasionally throughout the universe. Emptiness is the fundamental rule the universe is built upon, and galaxies, stars, and planets are simply the exception woven sparsely throughout it. Here's the trust signal worth remembering as we approach tonight's final stretch. All 3 voids we've explored are genuinely, independently confirmed through multiple separate research teams and multiple different survey methods. What remains actively unresolved is exactly how they connect to each other, exactly how significantly they influence our broader measurements of the universe, and exactly what still larger structures might still be waiting undiscovered, hidden somewhere out there in the depths of space. That question, what else might still be hiding out there, is exactly where we're headed as tonight's story reaches its final chapters. Here's the part of tonight's story that keeps cosmologists awake at night, and it has nothing to do with the size of any single void we've explored so far. It has everything to do with what these anomalies might be quietly telling us about the reliability of our entire cosmic model. Remember the cosmological principle from the very beginning of tonight's journey. The foundational rule stating that the universe should look roughly the same everywhere, once you zoom out far enough. That rule isn't just a minor detail buried somewhere in an astronomy textbook. It's one of the core assumptions holding together nearly every major calculation modern cosmology depends on. Here's why that matters so much. If our own region of space is measurably underdense, and if a completely separate, independently confirmed void sits perfectly aligned with one of the strangest anomalies ever found in the universe's oldest light, that's no longer just one isolated, easily dismissed coincidence. That starts looking like a genuine pattern, and patterns, in science, demand serious, sustained attention. Here's the honest, sobering question researchers are actively grappling with right now, in real time, this very year. What if the universe is measurably less uniform at these enormous scales than the standard cosmological model has confidently assumed for decades? And if that's genuinely true, how many of our other cosmic measurements, ones we currently treat as fully settled and reliable, might also need meaningful revision? This isn't scientists panicking or throwing out decades of trusted, hard-won work. This is exactly how careful science is supposed to function. When multiple independent pieces of evidence start pointing in a consistent direction, researchers have a genuine responsibility to seriously investigate, rather than simply dismissing it all as coincidence and moving on. Here's a comparison that captures the stakes involved. Imagine a massive, beautifully engineered bridge, one that has reliably held steady for decades without a single structural issue. Then, three separate, independent inspectors working completely independently of one another, each report finding a small crack in roughly the exact same support beam. No single crack is necessarily catastrophic on its own, but three independent reports, all pointing toward the same specific structural location, absolutely demand closer, more serious investigation. That's essentially the position cosmology finds itself in right now, this year. Our local hole, the Botez void, the Eridanus supervoid, aligned precisely with the cold spot. Three independent cracks, potentially pointing toward the exact same underlying structural question about how evenly the universe is genuinely built. Here's the trust signal that matters most here. Nobody has proven the standard cosmological model is fundamentally wrong, not even close. But the growing body of specific evidence pointing toward these unusual underdense regions has genuinely earned serious, sustained scientific attention rather than quiet, easy dismissal. And that serious attention leads directly toward one final, almost dizzying question. The one we're about to sit with together as tonight's story reaches its true climax. Let's lay every single piece we've built tonight out clearly, side by side, because the full pattern only becomes genuinely visible once you can see everything laid out together at once. Our local hole, roughly 2 billion light-years across, sitting right where our own galaxy happens to reside, potentially helping explain the Hubble tension, one of modern physics' most stubborn, persistent, unsolved puzzles. The Botez void, roughly 330 million light-years across, discovered decades earlier through nothing more than careful, patient survey work, revealing that massive cosmic emptiness isn't some incredibly rare exception, but rather a completely normal, expected feature of the universe's fundamental structure. The Eridanus supervoid, roughly 1.8 billion light-years across, sitting perfectly aligned with one of the strangest, most stubborn anomalies ever detected anywhere in the universe's ancient surviving light. Three separate voids, three completely independent discoveries made by entirely different research teams, using entirely different methods across multiple separate decades of dedicated scientific work. Here's the question worth sitting with directly. What if these three voids are not simply three unrelated, isolated curiosities, each existing in its own separate scientific silo? What if they're actually visible pieces of one much larger, still poorly understood underlying pattern, one that current cosmology hasn't fully mapped out and hasn't fully explained quite yet? Here's a comparison that captures this feeling precisely. Imagine slowly discovering three separate, seemingly unconnected puzzle pieces scattered randomly across a massive, empty table. Individually, each piece looks interesting enough entirely on its own. But once you finally manage to connect all three pieces together, you suddenly notice they're part of one much larger, unfinished picture, one still missing the majority of its remaining pieces. That's genuinely, precisely where cosmology currently stands with these voids, right now, in real time. Here's the honest, necessary trust signal as we approach tonight's true climax. We do not yet know for certain whether these three voids are meaningfully connected to one another in any deep structural way, or whether they simply represent three separate, ordinary examples of the same expected, well-understood cosmic web structure we described several chapters back. Both genuine possibilities remain firmly on the table, and this remains an active, unresolved area of serious, ongoing research. But here's why that particular uncertainty matters so much, and why it should genuinely excite you rather than frustrate you. We are living through one of those specific, exciting moments in scientific history, where the data has clearly outpaced the fully settled explanation. We can see the pattern forming clearly. We simply don't yet fully understand exactly what it truly means. And that specific kind of uncertainty leads directly toward tonight's single biggest, most far-reaching question of all. Here's the question tonight has been quietly building toward from the very first chapter. If our own galaxy sits inside one confirmed void, and that void might connect to an even larger pattern of voids scattered across the observable universe, could we possibly be living inside a bubble, nested within another, still larger bubble? Let's genuinely explore this idea properly, because it's not simply casual, idle speculation. It's a real, serious hypothesis some cosmologists have actively proposed and continue investigating. Here's the basic structure of the idea. What if the local hole isn't simply one isolated, standalone void, floating alone in an otherwise uniform, evenly distributed universe? What if it's actually one relatively small piece, nested within some much larger, underdense structure, one so genuinely massive that current survey technology hasn't yet managed to properly map its true full extent? Here's a comparison that helps make this concept click. Picture a set of Russian nesting dolls, each one hiding a smaller doll tucked neatly inside it. Our galaxy sits inside the local hole. The local hole might potentially sit inside some larger, still poorly understood underdense structure, and that larger structure might potentially connect to still other voids, like Eridanus, scattered elsewhere across the wider, mapped universe. Here's why cosmologists take this specific nested possibility seriously enough to actively investigate. Remember the cosmic web structure we explored a few chapters back? Voids don't simply exist as perfectly isolated, standalone pockets, sitting completely alone in space. They connect to walls. Walls connect to filaments. Filaments connect to other, entirely separate underdense regions elsewhere across the universe. The entire structure is deeply, fundamentally interconnected, not neatly isolated into separate, unrelated pieces. Here's the honest, necessary trust signal, and this part matters enormously. This specific nested bubble idea remains genuinely more speculative than most of what we've carefully covered so far tonight. It's an active, serious hypothesis under real investigation, not yet a confirmed, settled scientific conclusion. Current survey technology genuinely struggles to map structures at these extreme, almost unimaginable scales with complete confidence, which means definitively confirming or ruling out this specific idea will likely require future telescopes, ones significantly more powerful than anything currently available today. But here's why this particular question matters so much regardless of how it eventually gets resolved. If it turns out to be true, it would mean our current picture of the universe's overall structure is genuinely incomplete in some fundamental way, missing entire layers of large-scale organization we simply haven't detected quite yet. And that specific possibility, an incomplete picture of reality itself, leads directly toward tonight's final, most far-reaching question of all. We've arrived at the single biggest question tonight's entire journey has been quietly building toward, chapter after chapter. What if the cosmological principle itself, the foundational rule stating the universe looks roughly the same everywhere once you zoom out far enough, isn't entirely, perfectly correct? Let's be genuinely careful and precise here, because this is exactly the kind of claim that deserves serious, measured caution, rather than dramatic overstatement. Nobody credible is seriously suggesting the cosmological principle is completely fundamentally wrong. It has successfully predicted an enormous range of observations for the better part of an entire century, and it remains the single best working foundation modern cosmology currently has available. But here's the more careful, more precise version of tonight's question. What if the universe is simply less perfectly uniform than the standard model has generally assumed, not broken entirely, but genuinely, measurably lumpier at these enormous, previously underexplored scales than anyone originally expected? Here's a comparison that captures this specific distinction precisely. Imagine a professional weather forecaster confidently predicting that tomorrow's temperature will land somewhere around 70 degrees across an entire, sprawling state. That forecast isn't fundamentally wrong, but the real, actual temperature might still vary meaningfully by neighborhood, warmer down in specific valleys, noticeably cooler up along nearby mountain ridges. The overall big picture forecast stays broadly correct, while the fine, specific local details still genuinely, meaningfully differ. That's roughly, precisely the situation cosmologists currently find themselves navigating. The broad, sweeping picture of the universe stays fundamentally correct, but our own specific neighborhood, our own precise cosmic address, might be measurably lumpier, measurably less uniform than the simplest version of the standard model originally assumed. Here's why this particular distinction carries such enormous stakes for the future of physics. Nearly every major cosmological calculation, the true age of the universe, its ultimate eventual fate, the exact behavior of mysterious dark energy, all of it depends on assuming reasonably consistent uniformity at these extreme, largest possible scales. If that foundational uniformity assumption needs even a modest, meaningful adjustment, the ripple effects could genuinely reach into nearly every corner of modern physics. Here's the honest, necessary trust signal to close this particular chapter. This remains one of the most actively, seriously debated open questions in all of cosmology today, right now, in real time. Some researchers believe our specific local void findings represent nothing more than ordinary, statistically expected cosmic variation, requiring absolutely no fundamental rethinking whatsoever. Others believe these same specific findings hint at something genuinely deeper still waiting to be properly understood. Nobody currently knows, with full scientific confidence, which specific side of that debate will ultimately turn out correct. And that particular kind of open, honest, unresolved uncertainty is exactly what makes this entire story worth telling, tonight, right now, in this specific chapter. Before tonight's story reaches its true conclusion, let's look forward instead of backward for a moment. What actually happens to a void like ours, as the universe keeps aging, keeps expanding, for billions upon billions of years still to come? Here's the basic, well-understood mechanism at play. We already know voids expand slightly faster than the universe's overall average rate, purely because of that same uneven gravitational pull tugging outward from their denser surrounding walls. Over enormous stretches of cosmic time, that seemingly small difference compounds significantly, growing more pronounced with every passing billion years. This means our own local hole, and every other void, woven throughout the wider cosmic web, will likely continue growing steadily larger as the universe continues aging forward. Here's a comparison that makes this specific process click clearly. Picture a small, empty patch appearing somewhere within a slowly rising batch of bread dough. As the dough continues expanding outward in every direction, that specific empty air pocket doesn't simply stay the exact same fixed size. It grows right alongside everything surrounding it, gradually claiming more and more relative space within the loaf as time passes. Now stretch that exact same basic process across literally billions of years, and you get a genuine sense of how these enormous cosmic voids likely continue evolving, growing larger and larger as cosmic time marches steadily forward. Here's the part that carries genuinely significant, far-reaching implications. As voids continue growing across cosmic time, they'll likely become measurably emptier, while the surrounding, denser filaments and walls become correspondingly more tightly compressed, more densely packed together by comparison. Eventually, across almost unimaginable stretches of future cosmic time, some individual galaxies sitting near a void's outer boundary might become gradually, permanently isolated, drifting further and further away from any other visible cosmic neighbors. Here's the honest trust signal worth holding onto as we approach tonight's true conclusion. This general growth pattern, voids steadily expanding faster than the universe's overall average rate, is well supported by both careful theoretical modeling and detailed cosmological simulations. The specific long-term fate of any individual void, including our own local hole, remains considerably harder to predict with full, complete confidence, since it depends on several other cosmic factors that remain incompletely understood, including the true, still mysterious nature of dark energy itself. But here's the genuinely striking part worth sitting with for a moment. If this general pattern holds true, some unimaginably distant future civilization, living perhaps trillions of years from tonight, deep inside some far more advanced version of our own local hole, might eventually look up into their own night sky and see almost nothing else at all. No other visible galaxies, no cosmic web patterns left to properly study or discover, just their own single, isolated galaxy, floating alone inside an ocean of empty, silent space. That specific unsettling thought leads directly toward tonight's final, most important, most personal question of all. Let's ask the honest, necessary question directly. What actually happens to modern cosmology if these local voids ultimately do force some kind of genuinely meaningful revision to the standard model? Here's why this specific question matters enormously, far beyond simple, abstract scientific curiosity. The standard cosmological model isn't just one isolated theory quietly sitting on a dusty shelf somewhere. It's the deep, foundational framework underlying GPS satellite technology, our fundamental understanding of how stars are born and eventually die, and our current best predictions about the universe's ultimate, distant fate. Here's a comparison that captures the genuine stakes involved here. Imagine a massive, sprawling city, one built carefully over an entire century, layer upon layer, all resting on top of one single, foundational assumption about the specific composition of the ground underneath it. If new evidence eventually reveals that foundational ground assumption needs even a modest, meaningful correction, you don't necessarily need to tear the entire city down completely from scratch. But you absolutely do need to carefully, seriously re-examine literally everything built directly on top of that original foundation. That's genuinely, precisely the position modern cosmology finds itself in right now, in real time, this specific year. Here's what makes this particular moment in scientific history so genuinely exciting, rather than simply worrying or unsettling. Several serious, credible possibilities remain actively on the table simultaneously. Perhaps our own local hole, combined with the Eridanus supervoid, will eventually fully explain the Hubble tension, and the standard cosmological model will only require some fairly minor, modest local adjustments. Perhaps modified Newtonian dynamics, or some other still undiscovered alternate theory of gravity, will eventually prove genuinely necessary at these extreme, previously underexplored cosmic scales. Or perhaps some entirely different explanation, one nobody has even seriously proposed yet, will eventually emerge from future research still years away from being conducted. Here's the honest trust signal to hold on to as tonight's story approaches its true final conclusion. Nobody currently knows, with complete scientific confidence, exactly which specific explanation will ultimately prove correct. What we do know, with genuine confidence, is that the answer will very likely require significantly more advanced telescopes, significantly more precise, larger-scale survey data, and quite possibly several more additional decades of dedicated, careful scientific work. That specific kind of open, honest uncertainty isn't a weakness in tonight's story. It's genuinely the entire point of what real science actually looks like, up close, while it's still actively, genuinely happening in real time. Let's finally, properly connect all of tonight's journey back to you directly, because this story was never really just about distant, abstract space. You began tonight's journey sitting inside a hole roughly 2 billion light-years wide, without ever fully realizing it. You've now met a second void, discovered decades earlier by complete accident, so genuinely empty it fundamentally reshaped how scientists picture the universe's large-scale structure. You've met a third void, aligned almost perfectly with one of the strangest, most persistent anomalies ever properly detected in the universe's oldest surviving light. And you've sat directly with the uncomfortable, genuinely open possibility that our entire cosmic model might need some kind of meaningful revision in the years still ahead. Here's what all of that genuinely means for you. Tonight, right now, sitting exactly where you are, it means the universe you're living inside is measurably, genuinely stranger than most people ever properly realize. Not because of anything remotely supernatural or unexplainable, because real, careful, patient science keeps consistently revealing that our confident assumptions about reality are often significantly less complete than we originally believed them to be. It means your own specific location in the universe. The fact that you happen to exist inside this particular underdense stretch of cosmic space may have genuinely, measurably shaped the specific scientific questions humanity has been able to properly ask throughout our history. A civilization located somewhere else entirely might have developed an entirely different picture of reality, built from entirely different, locally available evidence. And it means some of the very biggest, most consequential questions in all of modern physics, questions like exactly how fast the universe is truly expanding, remain genuinely unsolved, right now, in real time, tonight, as you're sitting here listening. Here's a final comparison worth carrying with you well after tonight's story ends. Imagine standing directly at the genuine edge of a sprawling, mostly unmapped, uncharted forest. You can clearly see certain trees standing close by, certain specific paths already carefully mapped by those who came before you. But the overwhelming majority of that particular forest still stretches out entirely uncharted, waiting patiently for someone, quite possibly someone exactly your age, right now, tonight, to eventually walk directly into it and properly map what's genuinely there. That's precisely, genuinely where modern cosmology currently stands. We've mapped 3 enormous, confirmed voids. We've identified one of the most stubborn, persistent, unsolved tensions in all of physics, and we've barely, genuinely begun to properly understand what any of it truly, fully means. Here's tonight's final, honest, genuine trust signal, the one worth carrying with you long after this specific video eventually ends. Everything we've explored together tonight is real, careful, peer-reviewed science, not speculation or invented fiction. The specific meaning behind all of it remains genuinely, actively unresolved, unfolding in real time, in research papers being written and carefully reviewed right now, this very year, by scientists working literally somewhere on Earth. As you listen to these exact words, you live inside a hole in space. Nobody, including the world's leading cosmologists, fully knows yet what that genuinely, ultimately means. And somewhere out there, in a research lab or university office you'll likely never personally visit, someone is working right now, tonight, to finally help figure it out. Let's circle back to that nesting doll idea one more time, because there's a piece of it we haven't fully unpacked yet. and it might be the strangest piece of tonight's entire story. Remember, our own local hole might not be a simple, standalone empty region, floating completely alone through an otherwise perfectly uniform universe. It might connect to something even larger still, some genuinely massive, underdense structure that current survey technology hasn't yet managed to properly map in its complete true form. Here's why that idea deserves one more careful look before tonight's story fully closes. If our galaxy truly sits inside a void, nested inside some still larger, underdense region, and that larger region potentially connects toward other confirmed voids like Eridanus scattered elsewhere across the wider, mapped sky, then the actual boundary of our neighborhood becomes genuinely, meaningfully harder to define than most people ever properly assume. Picture standing in your own backyard, genuinely confident you know exactly where your specific property line ends. Then imagine slowly discovering your entire neighborhood sits inside a much larger, gated community you never even knew existed, one connecting towards several other separate communities you've genuinely never visited or properly explored. Your own personal sense of home doesn't disappear entirely. It just turns out to be one small, relatively modest piece of something considerably larger than you'd originally, confidently assumed. Here's the genuinely fascinating part scientists are still actively working through, right now, in real time, confirming whether these three separate voids, our own local hole, Boötes, and Eridanus, are truly, meaningfully connected requires mapping matter distribution across scales even larger than what current telescopes can properly, confidently reach. We're talking about survey volumes considerably larger than anything fully completed so far, requiring years of dedicated future observation time from instruments still being carefully designed and built. Here's the honest trust signal worth holding on to here. This specific nested connection remains a genuinely serious, actively pursued hypothesis, not a settled, confirmed scientific conclusion. Some cosmologists lean toward believing these voids are simply separate, ordinary examples of the same expected cosmic web pattern appearing in different corners of the sky purely by statistical chance. Others believe the specific alignment and comparable enormous scale of these voids hints at something more structurally connected, still waiting to be properly discovered. Nobody currently knows for certain which specific view will ultimately prove correct. But here's what makes this particular uncertainty worth sitting with. One final time. Every single major discovery we've explored throughout tonight's entire journey, the local hole, Boötes, Eridanus, the entire cosmic web itself, started out exactly this way. A strange pattern, an open, honest question. Years of careful, patient, dedicated work before any real, confident answer finally emerged. We may be sitting, right now, at the very beginning of figuring out exactly how far this specific pattern of emptiness genuinely extends. We end tonight exactly where we began, except now you understand precisely what that beginning genuinely fully means. You live inside a hole in space, roughly 2 billion light-years wide, and that hole is not standing still. It is growing, slowly, steadily, every single day, pushed outward by the exact same uneven gravitational pull we carefully traced several chapters back. The stretch of space around you is measurably becoming a little emptier, a little more underdense, with every passing year that quietly ticks by. Here's what makes that genuinely worth sitting with, one final time. This isn't some far-off, abstract process happening exclusively to distant galaxies you'll never properly see. It's happening directly to your own specific cosmic neighborhood, right now, in real time, while you're listening to these exact words. Tonight, we traveled through three separate, independently confirmed voids, our own local hole, potentially explaining one of physics's most stubborn unsolved tensions. The Boötes void, discovered completely by accident decades ago, revealing that massive cosmic emptiness is genuinely the rule, not some rare exception. And Eridanus, aligned almost perfectly with one of the strangest anomalies ever properly detected in the universe's oldest surviving light. We explored how scientists actually build three-dimensional maps from nothing more than stretched, shifted light. We sat directly with the uncomfortable possibility that the universe might be measurably less uniform than the standard model has confidently assumed for the better part of an entire century. And we asked, honestly, whether our own whole might connect to something even larger still, some structure current telescopes haven't yet managed to fully map. Here's the comparison worth carrying with you well beyond tonight. Imagine discovering, one ordinary day, that your entire house sits on ground that's been slowly, steadily sinking for years, just a few careful millimeters at a time, so gradually that nobody living there ever properly noticed. The house itself hasn't collapsed. Nothing feels obviously wrong from day to day, but the actual ground beneath your feet is genuinely, measurably different than it was when you first moved in, and it keeps shifting steadily further, year after year. That's roughly, precisely what it means to live inside a growing cosmic void. Nothing about your own daily life changes in any way you could ever directly feel or notice. But the actual structure of the universe surrounding you keeps quietly, steadily shifting, one careful measurement at a time, one dedicated research paper at a time, one small, incremental piece of the full picture at a time. Here's tonight's final, honest trust signal, the one worth genuinely remembering above everything else we've covered. Every single specific fact in tonight's story is real, careful, peer-reviewed science. The full, complete meaning behind all of it remains genuinely, actively unresolved, unfolding right now, in real time, in university offices and research labs scattered across the entire planet. You began tonight thinking you understood roughly where you stood in the universe. You end tonight knowing that even the world's leading cosmologists are still honestly, genuinely working that exact same question out themselves. The whole is real, the whole is growing. And somewhere out there tonight, someone is working hard to finally help us understand exactly what that truly means.